All right, welcome back. Hopefully everyone is here and is able to make it in through the waiting room. So we will be starting off with Santosh, talking about whatever the latest news is on the RLIBM project. So Santosh, take it away.
Oh, thanks, Bill. So today I'm going to talk about new results and also an overview of the RLIBM project. So where we have been building fast and correctly rounded math libraries. So let me tell you how I got started working on correctly rounded elementary functions, right? Long time my group had been working on compiler optimizations. We found floating point optimizations were wrong, and it eventually resulted in some applications producing wrong results. We spent nightmares debugging them. And when we built tools to diagnose them, we found math libraries to be wrong. And then they got amplified by other rounding errors and eventually resulting in wrong results. Well, we had nightmares debugging all these applications. So you may say, who cares? If you care about portability, reproducible signs, having correctly rounded libraries makes your life easier. So now we wanted to understand how correctly rounded libraries are implemented. Why are they wrong? So what is a correctly rounded result? Okay, so why is my... what is a correctly rounded result? So you have a real number line. So there are infinitely many real numbers, and any finite precision representation can only represent a few points here. V1, V2, 3. V3 are values that are representable in a floating point representation. When you call an elementary function, such as ln of x, it produces a real value. It's not exactly representable in the floating point representation. Then you need to round it according to the rounding model. Let's say round to nearest rise to even to a nearest floating point value. Here, V2 is the correctly rounded result. The goal with our elementary function is to produce this correctly rounded result. Now, let's see how do existing implementations of correctly rounded libraries, or generally mainstream libraries, produce results, right? Okay, so everyone uses results from approximation theory, right? Weierstrass theorem and Chebyshev interpolation theorem to approximate the real value of the elementary function that you have. And it turns out you can only do this over a very small domain. If you look at the slide here, you can do approximation over a very small domain. So you have an input, which may be very large. You need to reduce it to a small domain to make it to make this approximation feasible. And this process is called as range reduction. And once you have range reduction, what do? Use classic approximation techniques. So one such technique is minimax approximation. Over the small domain, you generate a polynomial that minimizes the maximum error across all points. And then you have the result from the polynomial, you evaluate it over this small input, you produce the result, and then you compensate it to produce the result for the original input. So effectively, you have three parts: range reduction, output compensation, and polynomial evaluation after you generate the minimax polynomial approximation. Now the question is, why do minimax approximations produce wrong results? So let's say we have an input, x1, whose result is very close to the rounding boundary. And what is the rounding boundary in the case of round to nearest rise to even? It's the midpoint. And when the real value is very close to the rounding boundary, the freedom that you have with a minimax approximation is very limited. Like in this case, the gray region is the freedom that you have. And if you have, now you can use the standard techniques such as RMS to bound the error to be within this region, right? So by using a higher degree or using a large number of terms. And then what happens? You need to do polynomial evaluation and output compensation. Any additional error will make you generate a wrong result. Okay. So what is the RLIBM project in a nutshell? The idea in the RLIBM project is, why are you focused on the real value? Just approximate the correctly rounded result. So RLIBM project makes a case for directly approximating the correctly rounded result. And now you may be wondering, man, how do I know what is a correctly rounded result, right? So this is why we split the problem of generating correctly rounded libraries into two parts. How do you generate an oracle, which requires you solving the table maker's dilemma? And then the second part is, once you have an oracle, how do you generate fast and correct implementations? The focus of the RLIBM project, given a slow oracle, such as an MPFR library, which people have built over decades of effort, right? So use that as an oracle and generate a really fast correctly rounded libraries. Okay. So now, like if you directly approximate the correctly rounded result, let's say you're generating a result for a 32-bit float, correctly rounded library for a 32-bit float. You would implement the library in double precision. So around the correctly rounded result, there are a lot of double values. You produce any value there, it rounds to the correctly rounded result. That is the freedom that you have for your polynomial approximation. And this freedom is much larger than the minimax freedom that we saw earlier. Okay, so this is called as a rounding interval. Now, using this idea of approximating directly the correctly rounded result and the rounding interval around it, like let's see how the RLIBM approach works in a nutshell. You have an elementary function f, and you have a representation and you have a rounding mode. Use the slow oracle to compute the correctly rounded results for all inputs. Okay, identify the rounding interval for each input. Okay, so this rounding interval for each input specifies a constraint on the polynomial that you're going to generate. What is a polynomial? When you evaluate the polynomial, it has to lie within the rounding interval. It should be greater than the lower bound, less than the upper bound. So you have a billion such constraints for each input. It's a system of linear inequalities. Polynomial is just like identifying the coefficients of with the degree d, right? D is it's an iterative process. So now you have a linear program. Use a LP solver to solve it. There you go. Okay, but modern LP solvers don't solve billion constraints. They time out. Okay, so what we observe is the linear program in the context of the RLIBM project is a linear program of small dimensions. Lots of constraints, but we're not looking for polynomials of degree billion, right? Like we're looking for polynomials of degree 5 or 6. So it's a linear program of small dimensions. We have a fast randomized algorithm to solve such LP problems. Here, PLDR paper for details. And then what is the end result of all this? You solve this linear program, you get a resulting polynomial that produces correct results for all inputs for the given representation in the given rounding mode. Oh, like would have been amazing if this was the only rounding mode and the only representation that you had, right? But there are 5 rounding modes in the standard. And today, like it's the age of machine learning, right? Everyone wants to design their own numerics representation. So wouldn't it be good if we have a single polynomial approximation that produces correctly rounded results for multiple representations and rounding modes? This is the next new result from the RLIBM project, right? Let's say you want to generate correctly rounded results for all representations from 10 bits to 32 bits, and with all 5 rounding modes in the standard. What is the secret sauce? Create a correctly rounded library for a 34-bit representation, 2 additional bits, with a round to odd mode using the RLIBM approach. And it magically produces correct results for all this. So what is this round to odd mode? The round to odd mode is a non-standard mode, which has been like used in the past, but no one has explored it in detail. So if a value is exactly representable in a representation, it rounds to that value. If it is not, it rounds to the nearest value that is odd. And if you use this, you get like amazing results, right? So again, our papers have a lot of details. I'm not in 10 minutes. I'm just giving you a flavor for it. Now, like is this all the stories that I'm making up, right? Does it even work? So we have built a collection of functions which are correctly rounded for a single polynomial approximation, produces correct results for thousands of configurations. Okay. And yeah, so you may be paying in terms of performance. Well, like at least in our experiments, we are like 50% faster than the fastest libraries out there, like and which produce like millions and millions of wrong results. Okay. And for me, like more gratifying thing is when people use my stuff. So we have been collaborating with folks who are building correctly rounded libraries, such as like Q Lee at Google, who has been like contributing to LLVM libc. We have pushed 5 functions and assisted him in pushing 5 functions into LLVM's libc, which are correctly rounded for all rounding modes. Okay, so to summarize, there is value in correctly rounding, in directly approximating the correctly rounded result. There is, I think, like as a maintainer, it's much more appealing for me if I have a single approximation that produces correct results for multiple representations and multiple rounding modes. And we at least have shown evidence correctly rounded libraries can be fast and correct for at least 32-bit representations. So maybe like in collaboration with the community, we mandate correct rounding for representations up to 32 bits. If this talk excited you to explore more about the RLIBM project, please go to the RLIBM project page. Papers, talks, and tutorials are all available from the page. And again, I'm just advertising. My students and collaborators are equal co-conspirators in this project. And thank you for your attention.
Yeah, thank you, Santosh. It's always extremely interesting to see the latest on this project. Zach has something he wants to say immediately. So.
Oh no, that's the clap emoji, Bill.
That's the clap. That's not the hand. Oh, I'm so bad
of MC. You got to learn the hand versus the clap. However, having taken the floor, one thing I was curious about is in the context of hardware design. What are the consequences of RLIBM's more efficient polynomials for like FPGA implementations of arithmetic?
Yeah, so that's an interesting question. So we have fewer multiplications and fewer additions. Like we have lower degree polynomials compared to whatever people have been doing. So I would assume they're like much faster than like whatever like correctly rounded implementations that people have. That said, like rounding mode is an interesting issue. Like hardware folks love round to zero because it's just truncation, and that gives them like rounding comes for free. So now you can easily customize RLIBM. The way I see RLIBM is like it's an infrastructure. Like you care about like representation X and represent rounding mode Y. Just customize it. Like you can get whatever cost benefit trade-off that you want. And some people like hardware folks also care about faithful rounding rather than correct rounding, like 1 alpha error. So extending RLIBM to do that for performance is like very trivial in my opinion.
Yeah. Because you just move the boundaries where it's finding the polynomials. All the machinery is the same, right?
Yeah, actually, so sorry, I don't want to take up all the air, but suppose you do faithful rounding. Presumably that makes the LP easier to solve.
So I would say it's not, the LP is not easier to solve, but like you can generate lower degree polynomials because you have larger freedom.
Cool. Yeah, I love this project. Super fun stuff.
Where do we start shoving the standards discussion along? I think it's time.
I think like Hugo is part of the core math thing, right? Like like I have been chatting regularly with Paul Zimmerman. So hopefully like we are building like with core math, like with RLIBM, various other things. We built enough evidence that now the standards committee cannot say, oh, fast correct rounding is like expensive, at least for like a single precision.
Yeah. Cool. All right. As always, are there more questions in the Slack? I see some stuff from Samir. Samir says that you can answer after the talk. So maybe in the interest of time, we'll move along to the next talk and